place, and this actually doesn't take part in the actual ventilation. There is also not only anatomical, there is also another dead space which is called as the alveolar dead space, which is basically those alveoli which are actually not taking part into the alveolar ventilation, apart from the
Anatomical
anatomical
dead
dead
space,
space
which is
which
in
is in
the
the
airways.
airways.
So
So
combined
combined
together,
together,
these
these
two
two
forms the
forms the
physiological
physiological
dead
dead
space,
space,
which
which
is
is
very
very
important
important
to
to
keep
keep
in
in
mind
mind
when
when
we
we
are
are
talking
talking
about
about
disease
disease
states.
states.
So we
So we
know
know
that
that
in
in
our
our
lung
lung
there
there
are
are
various
various
muscles
muscles
which
which
act.
act.
I
I
have
have
told
told
you
you
earlier
earlier
that
that
they
they
work
work
in
in
tandem
tandem
to
to
create
create
a
a
negative
negative
pressure.
pressure.
So the
So the
most
most
important
important
out
out
of
of
all
all
these
these
is
is
diaphragm. And
diaphragm.
why
And
I'm
why I'm
talking
talking
about
about
these
these
muscles is
muscles is
because
because
most of
most of
these
these
muscles
muscles
would be
would be
affected
affected
in
in
various
various
disease
disease
states
states
when we
when we
talk
talk
about
about
later
later
on
on
in
in
subsequent
subsequent
lectures
lectures
about the
about the
various
various
disease
disease
processes
processes
where
where
ventilation
ventilation
becomes
becomes
difficult.
difficult.
And
And
expiration is
expiration is
primarily a
primarily a
passive
passive
process,
process,
and
and
where
where
the
the
elastic
elastic
recoil in
recoil
the
in the
abdominal
abdominal
muscles
muscles
recoil
recoil
so
so
that
that
whatever
whatever
air
air
which
which
has
has
come
come
during the
during the
inspiration
inspiration
is
is
just
just
expelled
expelled
out.
out.
So
So
there are
there are
various
various
pressures or
pressures or
forces
forces
which are
which are
acting
acting
into the
into the
lung
lung
system.
system.
Many
Many
of
of
these,
these,
I
I
think,
think, you
you must
must
have
have
heard
heard
of
of
the
the
intrapleural
intrapleural
pressures
pressures
and the
and the
intraalveolar
intraalveolar
pressures. I
pressures. I
think
think
these are
these
the
are the
two
two
very
very
important,
important,
and the
and the
transpulmonary
transpulmonary
pressures.
pressures.
These
These
are
are
important
important
pressures
pressures
which we
which we
need
need
to
to
keep
keep
in
in
mind.
mind.
And
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 third,
third,
the
the
second
second
thing is
thing is
the
the
lung
lung
recoil,
recoil,
which
which
occurs
occurs
because
because
of
of
the
the
various
various
collagen and
collagen and
other
other
fibers
fibers
which are
which are
present
present
inside
inside
these
these
muscles,
muscles,
which
which
leads
leads
to
to a
recoil of
recoil
the
of the
lung.
lung.
So if
So
we
if we
look
look
about
about
these
these
mechanics
mechanics
during
during
the
the
resting
resting
stage,
stage,
you
you
can
can
easily
easily
see
see
that
that
in
in
before
before
the
the
expiration,
expiration,
your
your
intrapleural
intrapleural
pressures
pressures
are
are
uh, and the and your
and your
lung
lung
folds
folds
are
are
almost
almost
equal,
equal,
so
so
that
that
your
your
alveolar
alveolar
pressures
pressures
are
are
almost
almost
zero.
zero.
But
But
during
during
inspiration,
inspiration,
as
as
more and
more and
more of
more of
intrapleural
intrapleural
pressures
pressures
becomes
becomes
negative
negative
because of
because of
our
our
muscles
muscles
which
which
are
are
acting,
acting,
and
and
also the
also the
diaphragm,
diaphragm,
as you
as
know,
you
the
know, the
diaphragm
diaphragm
becomes
becomes
flattened,
flattened,
and the
and the
intercostal
intercostal
muscles
muscles
start
start
contracting
contracting
during
during
inspiration.
inspiration.
The
The
intrapleural
intrapleural
pressures
pressures
become
become
more
more
negative.
negative.
So
So
there is
there is
always
always
a
a
slightly
slightly
negative
negative
alveolar
alveolar
pressures,
pressures,
and
and
because of
because of
which
which
the
the
air
air
rushes
rushes
in.
in.
And
And
at the
at the
end of
end of
inspiration, when
inspiration,
the
when the
expiration is
expiration is
about to
about to
occur,
occur,
again
again
both
both
these
these
pressures
pressures
almost
almost
equalizes,
equalizes,
and the
and the
lung
lung
wall
wall
recoils,
recoils,
and
and
whatever
whatever
air
air
which
which
has
has
come
come
inside
inside
is
is
just
just
expelled
expelled
out.
out.
So
So
this is
this is
what
what
normally
normally
happens,
happens,
and
and
this is
this is
possibly
possibly
why
why
I'm
I'm
telling you,
telling you,
because
because
this
this
is
is
what
what
we
we
would
would
be
be
simulating
simulating
by
by
using a
using a
ventilator.
ventilator.
So
So
this
this
is
is
in
in
nutshell
nutshell
what
what
I have
I have
just
just
told you.
told you.
What
What
is
is
important
important
is the
is the
transpulmonary
transpulmonary
pressure,
pressure,
which
which
is
is
nothing
nothing
but the
but the
pressure
pressure
at
at
the
the
airway
airway
opening
opening
and the
and the
pleural
pleural
pressure.
pressure.
And
And
this
this
is
is
the
the
pressure
pressure
which
which
really
really
guides
guides
the
the
movement of
movement of
air
air
inside
inside
the
the
lung
lung
through
through
this.
this,
And
and
during the
during the
inspiration,
inspiration
it
it
becomes
becomes
more
more
negative,
negative,
so
so
that
that
more
more
air
air
goes
goes
inside.
inside,
And
and
during
during
expiration, it
expiration it
becomes
becomes
slightly
slightly
positive.
positive.
And
And
most
most
of
of
these
these
pressures
pressures
are
are
basically
basically
because
because
of
of
contraction and
contraction and
relaxation
relaxation
of
of
various
various
intercostal
intercostal
muscles,
muscles,
the
the
most
most
important
important
being the
being the
diaphragm
diaphragm
over
over
here
here
and the
and the
intercostal
intercostal
muscles.
muscles.
So
So
this is
this is
what
what
actually
actually
is
is
happening
happening
when
when
inspiration and
inspiration and
expiration is
expiration is
happening. You
happening. You
can
can
see
see
from
from
this
this
graph,
graph
the
the
alveolar
alveolar
pressures
pressures
during the
during the
inspirations,
inspirations
I
I
told you,
told you
become
become
negative,
negative,
so
so
they
they
go
go
down.
down
As
as
they
they
go
go
down,
down
because of
because of
more
more
intrapleural
intrapleural
pressures,
pressures
which
which
is
is
becoming
becoming
negative,
negative,
the
the
lung
lung
is
is
expanding and
expanding
the
and the
volume
volume
of
of
air is
air is
going
going
in.
in.
And
And
just the
just the
reverse
reverse
happens in
happens in
expiration,
expiration,
where
where
the
the
alveolar
alveolar
pressure
pressure
starts
starts
increasing.
increasing,
The
the
intrapleural
intrapleural
pressures
pressures
are
are
now
now
more
more
positive,
positive,
and the
and the
lung
lung
is
is
deflating
deflating
right
right
now.
now.
So I will show you through this pictorial diagram where at the start of inspiration, the pulmonary pressures are more negative. So what is happening is the volume of the air is increasing, or the volume inside the lung is increasing. But as the pulmonary pressures become more positive in the expiratory part, the volume of breath or the intrapleural pressures they start increasing, and the difference between the two is exactly the transpulmonary pressures, where the volume of breath is slight, they go on decreasing. So this is what basically is the respiratory physiology, which we try to emulate by using a ventilator which provide a positive pressure ventilation. So if you can see from here, like the inspiratory part becomes more negative. The intrapulmonary pressures, it goes below zero. This red line is the atmospheric pressure. So the pulmonary pressures, they become zero and then they become positive. The intrapleural pressures to start with are -4 and they become more negative during the inspiration. And then they reach the baseline of -4. And the volume of breaths are, if you can see from here, the volume of breath or the tidal volume increases during the inspiration as the air is going in, and then it decreases as the air is pushed out. So keeping this in mind, so this is what basically is the range of intrapleural pressure during which inspiration and expiration happens, and what is exactly seen in this figure over here. So this is the difference between these two pressures is basically what we call as the transpulmonary pressure, and which is depicted over here is the pressure difference between the alveoli and the pleural spaces. Right. So now the little bit about pulmonary mechanics. I think what happens during the flow and the movement of air. We all know that normally the gas goes in and outside bronchi, and then there is an alveoli where you need to inflate those alveoli to reach a certain target volume. And for this flow and for this inflation, you need pressure. So there's an equation where we all know that resistance is equal to pressure upon flow, and many of these equations will be utilizing in subsequent slide. And out of these two very important concepts comes, and one concept is the concept of compliance. And the compliance is nothing but it's the change in volume per unit change in pressure. So delta V by delta P is the compliance. That means in layperson, if I talk about, say, if I'm inflating a balloon, the amount of pressure I'm applying to inflate that balloon will depend on the compliance of that lung. So if I apply a little bit of pressure and the balloon inflates too much, that means with a certain degree of pressure change, the volume change is great. So the compliance is actually a good compliance lung. But on the other hand, if I apply too much of pressure and the balloon inflates a little bit, then probably this balloon is having a poor compliance. And these we'll be discussing in what states we can all see this. So this is basically pressure which the ventilator applies to push in air, which includes this formula, which means volume divided by compliance, and plus the resistance which the gas will meet during the passage through the various airways. So lung compliance is, I have already told you, is nothing but unit change in lung by unit change in pressure. And if you see this lung compliance curve, I think most of you who have worked in with ventilators must have seen this graph over there. A very important graph which has two parts. This is a steeper part, and other is the flatter part of the curve. And this is this part which is basically the part where we want to ventilate any child. And why it is because this part? Because if you can see slight change in pressures, if you see the intrapleural pressures change, your lung volume changes to a greater extent. So that means the child has a good compliance. On the other hand, if you try to ventilate a child over here, you change a lot of, or you put in a lot of pressure over here, but your change in volume would be very less. So if you try to ventilate at this part of the graph, probably the child is having a poor compliance or a lower compliance. So always we need to keep this in mind, that we need to target the steeper part of the curve so as to achieve a good compliance. And this is what basically is depicted over here. So the compliance is delta V by delta P. And if you can see this alveoli, if you push or flow in, it expands to a greater extent if you are ventilating over this part of the lung. And that's why, and if you go to this part, probably you will not be able to achieve this great amount of what you change in tidal volume. So it's basically a measure of distensibility, how distensible your lung is or how distensible your balloon is when you talk about balloon. And the total compliance would include your lung compliance and the thoracic wall compliance. There are two concepts, I think, which again crops up over here. If you see your ventilators, they will sometimes tell you compliance figures, and there is a normal compliance, which is the static compliance, and there is another compliance which is called as dynamic compliance. Normally, what we normally look at is the static compliance, which measures the distensibility of the respiratory system, and it is measured when there is no airflow. So common conditions which leads to a decrease in like compliances which we commonly encounter in our day-to-day practice includes consolidation, pulmonary edema, effusions, pneumothorax, obesity. So most of the common conditions which we encounter in our day-to-day life would lead to a decrease in static compliance. Mind you, need to remember that static compliance is a compliance which the ventilator measures and tells you when there is no airflow. And it tells you the distensibility or the elastic property of the respiratory system, both lungs and chest wall. But if we talk about, we'll be talking about dynamic compliance. Dynamic compliance is compliance when the air is still moving through the bronchial trees. So it reflects two things. It not only reflects your lung and chest wall stiffness, but it also reflects the airway resistance. So again, same graph which I have shown earlier. This is what it depicts. So if your dynamic compliance is increasing or it's getting poorer, then possibly the problem can lie both in lung and chest wall and the airway resistance. However, if your static compliance is getting poorer, then probably the problem lies in the elastic recoil of the lung or the chest wall. So I think two important concepts come over here. So there are various things which can happen if your compliance is low or high. Low compliance, which we commonly see in, I've already told you, these are the conditions which leads to decreased compliance. And many of these can lead to decreased FRC, that is functional residual capacity. There is increased work of breathing. Lung volumes are low, as in consolidation, collapses. There is a low minute ventilation and compensatory increase in frequency or tachypnea, which a normally child will exhibit when the tidal volumes or the minute ventilation decreases. On the contrary, if you talk about high compliance states, so we talked about low compliance states, then there are high compliance states where the lung is over inflated. There is incomplete exhalation. Your functional residual capacity and the total lung capacity is actually increased rather than getting decreased. There's a lot of airflow obstruction, air trapping, and there's a poor gas exchange. And this classically happens in conditions of airway obstructions such as bronchial asthma. So if we talk about from a ventilation point of view, both low compliance states and also the high compliance states are bad to ventilate. They're both difficult to ventilate and bad to ventilate. So we want to basically ventilate, as I've shown you on this part of the curve, which is the ideal part where we want to ventilate any child. So we talked about static compliance, dynamic compliance, and let us talk about the clinical relevance of it. So if a dynamic compliance, what I've already earlier enumerated is that if the dynamic compliance has decreased, whereas the static compliance have remained relatively unaffected, it means probably the airway is obstructed. So always look for these figures on your ventilator. So if this is happening, then probably look for it. Is there some block in your ET tube, or there is a heat moist exchanger blockage, or there is a kinking or bronchospasm or something like that which is happening. But if your static compliance and dynamic compliance are both decreasing, then it means that your lung is becoming stiffer, and that is commonly seen in conditions like consolidation, collapses, effusions, and child developing pulmonary edema. So if you take care of these two figures, which the ventilator will automatically calculate. Nowadays we have very good ventilators, most of these available, which are microprocessor based. I think most of these figures are quite commonly available in most of these ventilators. So after compliance comes the resistance. It is basically, again, when the air goes in through the narrow airway passages, there is a frictional force, and to overcome this frictional force, a resistance is required, and this is what we call as peak inspiratory pressure, which we adjust on the ventilator. So if you pass air through a coiled tube like a lung, we know that it is the pressure which is required to deliver a given flow of gas, and this is generally shown by this simple formula where resistance is change in pressure, that is pressure P1 minus P2 over the flow, and this tells you the amount of resistance you will have to encounter when you pass a gas through a narrow tube. And this is basically gives you an idea of the peak inspiratory pressures. Now, if we are talking about pressures, there is another important concept comes, which is the concept of time constant. I think very important for you to understand what is the time constant. And time constant is the measure of time which is required for the alveolar pressure. Mind you, we are mainly concerned about the alveoli, where actually the gas exchange occurs. So once we are pushing into air through a ventilator, the alveoli will start inflating. So it is the time required for alveoli pressure to reach 63% of the change, or 63% of these alveoli to get inflated. But what we want is that at least 95% should get inflated so as to participate in gaseous exchange. So that's why we need at least 3 time constant if you look over here, and maybe 3 to 5 time constant if you want 99% of the change in pressure. So that is why it is important for you, and why this concept has come, because this time constant will decide about your inspiratory time. So normally we tend to keep our time, the inspiratory time, about 3 to 5 times of a time constant. And this is basically what this picture depicts you. This is a normal lung. The time constant is, suppose, particular. So once you have put in air, the alveoli opens up. This is the time constant X for this lung. But if the child have a low compliance, you push in air, but you need more time to really expand, because your lung has developed low compliance. So in that case, your time constant will change. And similarly, if there is a high resistance pressure, suppose there is an obstruction over here, your time constant will increase, because it has to now pass through this narrow passage to inflate this lung. So here, low compliance states, your time constant decreases, and in high pressure states, just as bronchial asthma, bronchiolitis, your time constant increases. So just this to keep in mind. And ventilator is a machine, I think, which we all know that generates pressure to cause a flow of gas to increase the volume. So it is a machine which uses these concepts which I have just told you to generate a pressure. It generates a pressure which causes a flow of gas from its end towards the alveoli, and so as to increase the volume of the lung, or what we call as the tidal volume of the lung. And this is, I think, I've already told, the pressure is volume upon compliance plus resistance plus, but you know that there are ventilatory tubings and other circuits. So pressure is also required to overcome resistance or flow through these ventilator tubings. So it adds on to the total amount of pressure which is actually required to flow the gas through and increase the volume of the lung. So if we talk about mechanical ventilation, we know there are two types. We are not going into the details of these types, because this is a whole lecture in itself. So what we basically would be talking about invasive ventilation, which is usually given through an endotracheal tube or tracheostomy tube, and non-invasive is which is not given through an endotracheal tube or tracheostomy tube. So this is what happens. This is the patient. He is intubated. You have corrected a circuit over here. So this is a ventilator through which the oxygen and air are blended. So there are various valves, assemblies over here, which allows the flow of this mixed oxygen mixture to go into one way. So this is the inspiratory limb, and all these processes are controlled by a control panel, which is microprocessor based. And once you fix a particular values, this ventilator will deliver the gases at a preset temperature, at a preset humidity, at a preset volume into this lung field, and whatever passively the lung fields exhale would come out through this into the expiratory limb over here. So this is a closed loop control, and this is what happens in a normal inspiration and an expiration of the lung. So there are many indications. I think we will not be going into the detail. Any child who is not breathing or is not breathing enough, you need to ventilate the child. Any child who is becoming hypoxic or hypercapnic, possibly he would require ventilation. Patient breathing with normal, but there is hard work of breathing, as in conditions with pneumonias, bronchiolitis, and all those respiratory conditions where there is increased work of breathing, and you think that the child is really going to tire out very soon. Probably you would like to give him certain rest to his respiratory muscles and intubate him. Airway protection is another. Do not almost, I think the most important out of all these is this equation. I think this will come time and again whenever we talk about ventilation, and this is called as alveolar gas equation. And we'll be talking you about this alveolar gas equation subsequently, where your partial pressure of oxygen at alveolar level is decided by the amount of FiO2 you are giving, the atmospheric pressure which has been applied, the pressure of the water vapors, the partial pressure of CO2 at the alveolar, at the arterial level, and a constant. So many of these values would be put into, and you will get a PaO2, which is a very important parameter to know when we are talking about ventilation and oxygenation. Right, so mechanical ventilation, we have certain volume control parameters. There are pressure control parameters like respiratory rate, PEEP, FiO2, tidal volume. And then let us see how do we go about these modes. So just in brief, we'll be talking about, besides this respiratory physiology, we'll be talking about now how this respiratory physiology is applied to give various modes or basic modes of ventilator, what we use commonly in our day-to-day life. So we have certain terminologies. I think we need to be very clear while using these terminologies. What are variables? What are various modes? It's a control versus spontaneous modes. What mode to use when? I think this is a lecture in itself. But what I will be doing in this talk is just to give you a basic sensitization about these basic entities. So we all know about peak and expiratory pressure. This is the pressure which is applied at the end of expiration, and the beauty about this is that it helps in preventing the collapse of alveoli and the airways. And obviously when this helps in preventing collapse, it helps to improve oxygenation. There's another pressure which we commonly apply in ventilators, and that is called as the PIP, or the peak inspiratory pressure. And it is basically the pressure which the ventilator applies to deliver a certain breath to achieve a target volume and certain parameters to deliver gases. And basically it is a sum of your PEEP plus the delta pressure. I think I'll be showing you in one of my slides what do you mean by delta pressure. And the area under this curve is basically what is called as mean airway pressure, which determines your oxygenation, and it depends on many things like PIP, PEEP, inspiratory time, and expiratory time. An important concept to know is plateau pressures. Now, what are plateau pressures? Plateau pressures are pressures which are needed to maintain lung inflation when there is no airflow. And this is actually the pressure which is being applied by the ventilator at the alveolar level. And this is actually we want to know, because most of the pressures like the PEEP or the PEEP, all these pressures are applied to the airways. And we are not very much clear that what is the exact pressure which is being applied at the alveolar level. So the plateau pressure is one pressure which is applied at the alveolar level, and it is measured at the end of inspiratory pause. So if we see from this diagram, this is the amount of PEEP which has been applied. And this is, if you see this going up is your inspiration. This is the top, which is the PIP or the peak inspiratory pressure, then it drops. And this is the plateau pressure. And the difference between these two is important to give you certain informations. And finally, it drops down, and this is a passive expiration. And again, a child takes a spontaneous inspiration, and then he takes a small breath. So this is basically a prototype of what actually happens in a pressure time waveform when a child takes a breath and is assisted by the ventilator. So there are various things which we need to know: the pressure support, the respiratory rate. We know what the ventilator is programmed to give to the patient. Inspiratory time is the time which the ventilator will deliver an inspiration. Expiration is mainly positive. Tidal volume is normally the amount of gas with each breath, and normal tidal volume is about 5 to 6 or 5 to 8 ml per kg of the ideal body weight. And FiO2, we know what we said is the amount of supplemental oxygen which is required so as to maintain a target saturation. We'll talk about trigger and cycling, but let us see that trigger is something which initiates the breath. How do ventilator know when to initiate the breath? So trigger is something which initiates the breath, and there are various parameters which are used to trigger. Cycling is one when the program is allowed to cycle from inspiration to expiration. So if we talk about various modes, there are various variables which need to be understood first: the control variables, the phase variables, and conditional variables, and finally the breath. And the control variables are what? It's the primary variable that the ventilator utilizes to produce the inspiratory phase of the mechanical breath. For example, what is the ventilator controlling to produce that particular breath? And as you know, there is a pressure, the volume or flow. So ventilator can control any one of them directly, but it would be only one at a time. So this is a control variable. So a ventilator could be having a pressure control or a volume control or a flow control. Now we talk about phase variables. I think this is the most important to understand what are phase variables. And what are phase variables are the parameters which are required to maintain and utilize to initiate a breath, to sustain a breath, to terminate a breath. And there are therefore 4 phases of breath. So initiation of inspiration, maintenance of inspiration, end of inspiration, and finally expiration. These are 4 cycles, or what you say 4 phases of breath, which are controlled by various variables which include again flow, pressure, time, all these things. So this is what we call as trigger, limit, and cycle variables, and we'll be talking about this in subsequent slides. Why I'm emphasizing this, because most of the ventilators, when you will go through, will use these terminologies to describe their modes. Conditional modes or conditional variables, I think, were used earlier where but now with the use of microprocessor based ventilators, they are not very commonly used. So these are ventilator variables like which which are changes are detected by the ventilator when a certain threshold is met, resulting in a designated output. So these are not commonly nowadays talked about. What is important for us and you to know is the control variables and the phase variables, and we'll be seeing this in subsequent slides. Another concept comes of VQ mismatch. So what has actually happened in over here is this is an alveoli, as you can see, and a deoxygenated blood is coming and an oxygenated blood is going. So this is happening normally. So in that case, your VQ means ventilation perfusion is normal. But what happens, look over here, what happens when your alveoli or your this bronchi is or the part which is taking part in oxygenation collapses. So what happens? In that case, your blood is coming deoxygenated and it passes on same. It's not getting oxygenated over here because your oxygenation machinery is bad over here. There is no oxygen which is coming through here. So this is called as shunt, because your blood is shunted through an alveoli which is not participating in oxygen. So this is called as shunt. On the contrary, the reverse happens when your vessels are not proper or they are not bringing good blood, but your alveoli are perfect. So the oxygen is coming, but the deoxygenated blood is not coming over here. So this is what is called as classically the dead space. And in ventilation, we need to prevent both these conditions and to take over these conditions. So ideal VQ is 1, but if you are dead space ventilation, your VQ increases or ventilation perfusion increases, and if it's a shunt, your VQ or ventilation perfusion decreases. And that is what we do, ventilators do, is to keep this alveoli open. So they apply pressures like PEEP to open up this collapsed alveoli and to help this alveoli participate in gaseous exchange. So the ultimate aim would be to have lung recruitment or to recruit alveoli. So now there are various modes. I think we all know there is a spontaneous mode where patient is taking breaths. Both the rate and the power is given by patient. There is a control mode, I think, where both the rate and the power is given by the machine. So totally controlled by the machine, here totally controlled by the patient. There is an in-between mode also, which is called as assisted mode. Here, part of the rate is controlled by the patient himself, but it is supported by machine. Machine means ventilator. So this is, and there is another mode apart from these three modes, which is called as assist control mode. And where in this mode, some minimum rate is provided by the ventilator. The rest additional respiratory rates are provided by the patient, and of course the support is given by the machine. So it's a combination of an assisted mode and a control mode. So this is what happens. So these are the various parameters we control: the pressure, the flow, the volume. Mind you, when we talk about volume, it is nothing but flow only, because volume is flow into time. So volume is sometimes when we talk about control variables, volume and flow are interchangeably used. So whenever we push in volume or flow through this, the lung inflates, and this is the pressure which is required to inflate a lung. So what controls a breath? There could be volume targeted ventilators when you target a particular volume or flow, tidal volume, or a pressure targeted where you target a certain pressure. And then we talk about now phase variables. So we talked about phases of respiration. So first is initiation. So how do ventilator know that you have to start, or the patient needs to start inspiration? So this is what is called as trigger. So this is trigger. Most of the times this trigger could be a pressure trigger, or it could be a time trigger. By what I mean is a particular time has elapsed, suppose you put in inspiratory time of X seconds. So after that X seconds have expired, the ventilator automatically knows now that the expiration has occurred, and it will, after that time period, it would automatically initiate an inspiratory breath. So this is time triggered. It could be pressure triggered, it could be volume triggered. Then the second time comes the limit. How the ventilator would limit that inspiration? Again, this limit could be a volume limit that you have set a target volume. It could be a pressure limit, or it could even be a time limit. Then we talk about when this inspiration turns to expiration, and this is called as cycling. That when the ventilator switches from inspiration to expiration, and finally expiration comes where you already applied a PEEP. So I think these are some of the trigger variables. It could be machine time triggered, patient triggered, sensitivities we have to keep, and then limit variables. Cycle variables are those variables which terminate the inspiratory flow. It could be volume again, it could be time, it could be flow in different modes of ventilation. So quickly talk about I think control mode of ventilation. In control mode, I think, as the name suggests, every breath is supported by the ventilator. And it is time triggered, if you remember over here. Time triggered. So what do you mean by time triggered? That the inspiration is started after a time period which is set by you on the ventilator. It could be volume or pressure targeted, and therefore it could be a guaranteed volume or a pressure. And this can be very easily seen from these graphics. If you see over here, this is a volume target, and if you can see over here, the flows are flat. That means this is a volume which you have targeted, and your pressures are going in inspiration and then expiration, and similarly the volumes. So this is what classically is seen in volume targeted ventilation, where you have a square flow pattern in your graphics. But there is another mode which we talked about, where assisted mode, where every breath is supported by the ventilator. Again, it could be pressure or flow triggered, and if you can see from here, there is a negative deflection over here. So what do you mean by negative deflection? This is the deflection which when a patient takes a breath which is detected by a ventilator, and as soon as it is detected by the ventilator will give its breath. So this is what is called as triggered breath. So here it could be pressure triggered. So there is a change in pressure over here which is sensed by the microprocessors or sensors in the ventilator, and it gives a breath. So this is called as assisted breath. Same thing is seen in assisted mode, and if you can compare it with the control mode, there is no negative deflection. All the breaths are totally given by the ventilator. So if you want to provide support through a ventilator, it could be complete, like in children with Guillain-Barré, where you don't need any support, there is no respiratory drive, there is severe fatigue, cardiorespiratory shocks, other things where you need a complete ventilatory support. Partial you would probably require in weaning and recovering from respiratory fatigues. So this is classically an assist controlled. We talked about assisted mode. Now we talk about assist control mode, where the ventilator is not only assisting but also controlling the breath. And what do we mean by just listen very carefully? This is what is a negative deflection. Over here you can see the negative loop going down, and this is what will be sensed by the microprocessors of ventilator, and it will give a breath, and it will support a breath. You can see very beautiful inspiration, expiration and expiration are coming over a period of time, which is your inspiratory time. Now here there is no negative deflection. So that means the rest, if suppose this breath is going below what you have set on your ventilator, then the machine will take control and it will give its own breath. So this is what is called as control breath over here. So these are assisted breaths over here, and this is a controlled breath. So that's why this mode is called as assist control mode. So you can see over here. And if you see over here, the volume is almost the same because it's a volume controlled volume targeted ventilation over here. Right? So we have targeted a certain volume, and to achieve that volume, once the patient triggers, the ventilator delivers a set target volume to that patient. And if it doesn't trigger, the volume is already preset to deliver a controlled breath. So now another mode comes which is called as IMV mode, or intermittent mandatory ventilatory modes, which is another mode where again your spontaneous breaths are being assisted with the ventilatory breaths, but not the breaths which are set above the supported breaths. And on top of that, it has also synchronized with it. So if you can see over here, in this volume targeted ventilation, let us make it more clear over here. These are some of the spontaneous breaths which are occurring. And this is one breath over here, which is again being sensed by the ventilator, and it delivers a breath. And then there are in between some spontaneous breaths. And then this is, if it doesn't sense a breath, then it provides a mandatory breath or a controlled breath. So this is what is happening in this SIMV. The patient is allowed to take his own spontaneous breath. As you can say, this is a spontaneous breath, this is a spontaneous breath. And if you see over here, during the spontaneous breath, the tidal volume is quite low because your lung plays bad. But once it provides an assisted breath, then it reaches your target volume. And when it provides your control breath, it again reaches its target volume. So again, this is particularly a mode which is more required when you are planning to say wean off a child. So this is what I have depicted. So what are the differences between these two modes, the control mode and the SIMV mode? Here every breath is supported regardless of the trigger. There is a risk of hyperinflation, and there could be some chances of patient ventilatory synchrony. But in SIMV, there is a potential of increased work of breathing because all the breaths are not supported. There are high chances that the patient might develop discomfort and asynchrony, and it's sometimes used as a weaning mode. But yes, obviously not a very good, because you would not like to have increased work of breathing in a child when you are trying to wean, and you would not want his respiratory muscles to get fatigued. So nowadays, people have started using SIMV with pressure support, where they give a certain amount of pressure to those spontaneous breaths, which possibly helps to overcome this patient discomfort, and which is a better modality to wean patients rather than using SIMV alone. Another is pressure targeted. I think we all know what is pressure targeted, where the pressure is limited. It is again time cycled, triggered by time of pressure. You set an inspiratory and expiratory time, and this is what is classically seen in a pressure targeted. There is a decelerating kind of flow which is seen over here, and a square pressure waveforms, if you can see, because your pressures are fixed over here. Similarly, in assist control, you will see there's a triggering over here, but your pressures are fixed as they are square. And if you see the flow, there's a decelerating flow kind of pattern which is seen in pressure targeted. Again, if you talk about pressure versus volume, pressure they deliver a targeted pressure, volume they deliver a targeted volume. There's a variable tidal volume, there's a variable peak inspiratory pressure, there's a decelerating flow pattern which is said to be more alveolar friendly. There is a square wave pattern, and this is sometimes commonly used in most of our clinical practice. Finally, pressure support, I think, which is basically a mode which is used by we use during the weaning phase. It is pressure targeted, patient triggered. The patient triggers himself or herself when to start the inspiration, but it is flow cycled. When the inspiratory flows decreases less than 25%, the inspiration changes to expiration. It is more comfortable for the patient, and also you can use it combined with nowadays it is available combined with your SIMV modes to help decrease or minimize the work of breathing. So these are various flow patterns. I think in itself it's a different class, but just to sensitize you that there are various graphs available on your ventilator which can sometimes give you an important information and also tell you about the various modes. Like this is a volume control mode. How do we know that? Can anybody tell how do we know this is a volume control? Anybody can answer in the chat box. How do we know that this is a volume control? Anybody? Am I audible?
Yes, audible.
Right. So anybody can tell me, like we just talked about various modalities, various modes. So anybody can tell on the chat box why we call it a volume control.
They are already writing on the chat box.
But I'm not able to.
Yeah, you go to the chat box.
Chat box is not visible here.
Yeah. You click the.
Go to the top next to the strawberry diagonal arrow. Just have to click on that.
I'm not able to see.
But when you go to the bring your cursor to the top of the screen, next to the strawberry diagonal arrow.
There is no diagonal arrow over here.
Next to the stop, sir. Are you able to see the stop?
I have to stop sharing.
No, next to the strawberry arrow sign.
Next to the stop. I'm not able to see.
There is a figure of a person, line figure of a person. You click that. Is there?
No, sir. I'm not able to see any figure. I'm only able to see notes written, comment written, and nothing else is coming.
Is there no option, sir, on this screen?
No, there is no option. Only my presentation is visible. Nothing else is seen.
मिनिमाइज करके देखो थोड़ा सा एक बार. जस्ट मिनिमाइज करो. अब आया?
मिनिमाइज में चैट में.
हाँ देखो चैट.
Okay, yes.
Got it. हाँ देखो.
So I think most of you are right. Somebody has said square waveform, fixed volume square. Yes, delivering volume is constant. Square waveform. Yes. So if you can see from what I have shown over here is the first is a volume control. As you can see, the flow is constant over here. So whenever in your waveform, if you find this kind of square flow waveform, it's a volume. It's a volume control. Sorry. So it's a volume control. The next one is, what is the next one? Anybody? If you can tell me what is the next one? Audio not available. Audio. It's available.
Yeah, clearly audible.
So yes, somebody has written very rightly. So why do you say assist over here? See a small amount of deflection over here. Can you appreciate? There's a small amount of deflection. This is what the ventilator detects to provide assistance. So this has, as many of you have rightly told, it is a volume. First is volume control, and this is a volume assist. Now what is the third one? Can anybody tell? Look at the waveforms. So what is the third one? Pressure control, okay. So many of you have written right. So if you can see from here, and if you appreciate, your pressure waveforms are square. Here the flow waveform was a square. Here the pressure waveform is square, so that you have set a pressure over here, which the ventilator is going to deliver at different tidal volumes. If you can see that your tidal volumes are changing. So this is what is called as pressure control. And the next is pressure assist mode. You can again appreciate a small amount of deflection over here, which is sensed by the ventilator. And then this ventilator provides an inspiratory inspiration followed by an expiration over a designated period of TI. If you see TI, that means your inspiratory time. So this is a pressure assist pressure control mode. And the third and the fifth and the last one is the pressure support mode, where everything is done by the patient itself. Here, everything, if you can see, there's a small beak over here, which is what pressure the ventilator senses, and it provides a breath over here. And similarly, it is when the flow decreases, when the inspiratory flow decreases, it automatically senses. If it is less than say 25%, then it automatically triggers the breath and an expiration starts. So this is totally a patient-controlled maneuver. So just to summarize some of the important modes in the end, you have controlled mandatory ventilatory, where everything is done by the patient. Assist control can be again volume limited and pressure limited. We have only two things: either we limit volume or we limit pressure. And this is again done for each and every breath. Then we have intermittent mandatory ventilation, which is again volume limited or pressure limited, and we have various triggers, cycling. So remember TLC: trigger, limit, and cycle. And then this is finally the pressure support mode, where everything is pressure limited and patient oriented, and it is done by the patient. It's triggered by the patient. If you can see, it is triggered by the patient and terminated by the flow, pressure, or time. And finally, there are other few modes like CPAP. It is not exactly a ventilatory mode, but it is a mode which is available in most of the ventilators now, where we provide continuous positive airway pressures. And this is again a mode which is used in weaning processes. So I think these are some of the basic modes. What I have done through my presentation is give you a brief idea about what is the basic respiratory physiology, what are the basic things to be kept in mind, what are the various variables which are to be kept in mind, what are the various parameters to be set, and what are the different modes, the more conventional modes, not talk about some higher modes which we use. So possibly just a sensitizer or a teaser to what ventilation is and what are the ventilatory modes. Thank you very much. I will be happy to answer any questions.
Thank you, Dr. Shalu. It is very, I should say, very comprehensive talk, explained in a very simple language. As you rightly told, it is more of a sensitization, and I'm sure everybody is supposed to know. Though most of them are doing as they have been told by the seniors what they have learned. Probably only few have actually explained the basics of ventilation. I'm sure if there are many questions, so you can go to chat box and answer those. Thank you so much. Before that, just an announcement for the BCA student. The exam pattern is almost finalized. If possible, I will take a class next time, or if not, next to next Friday. So be prepared for that. Or the diploma students who will be appearing in December exam. Over to you, Shalu, please. Thanks.
Yeah, thank you, sir. So, is how many pressure support? Again, see, most of these pressures, see, these are many of these pressures. I think if we take a class later on, we'll be telling you how to. There is no fixed number to put in a pressure like pressure support or peak inspiratory pressure and all those things. You have to start with the pressure, and then you have to titrate depending on your clinical conditions, your blood gas parameters, your target, what you want to achieve through that. Suppose there is a child who is having pneumonia and there is a problem in oxygenation. So whatever is your target is to maintain a saturation of maybe more than 92% or 94%. So if you start with some one setting, you apply a certain amount of pressure or volume depending on what mode you have chosen. And if you're not able to achieve that desired effect, then probably you need to hike up your settings and achieve that target volume. So a particular numbers to say what pressure support we should use is difficult to say, but yes, people have used pressure support with SMV according to the size of the endotracheal tube they use, and which can be somewhere around say 10 to 12 to start with, and then you can titrate it. So this is what how do they do. But again, there is no fixed number I told you for any particular disease, and as we know that every disease process is a very dynamic process. The child who has a pneumonia might develop say ARDS down the line, or he might improve. So your ventilatory settings, which probably you have started initially, would not remain same throughout. You need to titrate your settings according to what is happening to the child. Right, so that's happening. And how to titrate pressures in IDET? I think it's a very important question. Again, you need to define your goals in ARDS. What are your oxygenation goals? What are your ventilation goals? And then depending on your goals, you need to increase or decrease your ventilator settings to target that goal. But mind you, always whenever you are ventilating a child or an infant to achieve at a particular goal, there is one important thing which always should be kept in the mind is the concept of VILI, that is ventilatory induced lung injuries. We are sometimes too over enthusiastic to achieve our targets, so that we just skip that thing that these ventilators or these pressures or these volumes or these flows or those or these inspiratory times which we are giving to a child or a lung can sometimes be counterproductive. So there is another concept which is now evolving is ventilator induced lung injury, or the mechanical power concept which is coming, which now people are more and more concerned, because these ventilators are probably doing good, but they are also doing a little bit of harm. If somebody asked static and dynamic compliance, so it is calculated by the ventilator itself. If you apply inspiratory pause, you will get the static compliance, and dynamic compliance will keep on coming. And basically, if you look at static compliance, it tells you about the compliance of the lung and the chest wall. What compliance means? Say elasticity. And dynamic compliance is basically your airway resistance plus your chest and lung wall compliance. So it's a combination of both static plus airway resistance. So that is there. So I think it's how to set a ventilator. Probably I think it's a different class. We would probably think of taking a class of how and what are the parameters according to the various disease processes we need to set initially, and then how do we titrate. Management of ARDS and management of ventilator in an ARDS is again in itself is a different ball game, where we need to look into various kind of pressures. There are various ventilatory modes which I have not touched about over here, where people have used in ARDS, for example, APRV modes and high frequency oscillatory ventilations. I think these are some of the modes which people have tried using in ARDS, and that's why I said that treatment of ARDS is something different, which probably needs an extra class for that. So weaning off, yes, how to decide on weaning off? I think the first and the most principal concept when you should start thinking of weaning off is that once your primary disease process is over, like for example, if a child is admitted with pneumonia, and once down the line, 3 days, 4 days after you see that the child, that radiological picture is started improving, the child has become clinically stable, he's becoming afebrile, he's started accepting feeds, your ventilatory settings have started decreasing, maybe your read FiO2 of let's say 40% or 35%, then possibly I think this is the time when you should start thinking of taking him off a ventilator. And I think another very important concept of putting on a child on a ventilator is that whenever you put a child on ventilator, please start thinking of taking him off also. And that is why important that it is always said that putting on ventilator is easier, but taking him off is difficult. So always, every day when you come in the morning rounds, always think at the back of your mind, am I going to wean off this, or am I able to decrease the settings and take this child off in next couple of days? So this is something important. Putting on ventilator is easy. Anybody can intubate and put on ventilator. But the most important part is how judiciously you can titrate your settings and take him off as early as possible without causing any further injury to the lung or ventilator-induced lung injury, which I have told earlier. So that is basically the importance of ventilator. So ventilator is a temporary stopgap measure just to support your organ system for a couple of days or maybe hours till that time the child recovers. So that is an important thing which should be kept in the mind, that it is not a permanent solution, or it's not the treatment of the disease. Any questions? No, it is not necessary to provide nebulization while weaning. It all depends on what are the signs here. If your child has say bronchial asthma and you're finding on auscultation wheezing, then probably you will try to provide certain nebulization while weaning of this child. And many of the ventilators now, new ventilators, they come with an inline nebulizers which can be easily given. Sedation in ventilation, again, these are different topics, I think, which need to be tackled. How to sedate, when to sedate, what are the drugs to be used for sedation. I think this class was simply about your sensitization of what are the respiratory mechanics, what are the various terminologies which are used, how does a ventilator help, and what are the initial modes, just the initial modes to use with. How to decide where to set trigger? I think trigger is something which is already there on most of the ventilators. Then it is decided according to the clinical condition of your child. How to get recorded videos? This possibly, I think, Dr. Basu would be able to answer. I'm not sure.
This is in the domain of National Board. I am not involved in any recording, any forwarding. It is solely at the discretion of National Board. You can write with them directly. I'm sure Saurabh, you will agree with that. Thanks.
Yes, yes. Okay. Right. So I think any further questions related to these topics which I have just discussed? I know ventilation is a huge topic and it covers many things which I have not even touched here. But yes, this is just an initial teaser. Maybe we can go to further higher levels of ventilatory modes, ventilatory settings, disease-specific ventilation, what to do on ventilation, how to monitor on a ventilation, what all to look when there are alarms on a ventilation. So all these things probably would be covered in, maybe we can take further down the line.
Okay, I think we should. Yeah. Now, next class is on Friday as usual. Only thing, I might, if I get a nod from the National Board, I might take a class how to take the DCH, diploma exam. The batch have started. Those in MD doing their so-called degree course can also join, because I'll get a general idea, and I'm sure we'll get to know in a day or two, or in the next class I will take it out. So our day is fixed. It is on Friday, 7:30 to 8:30 p.m. unless it is a national holiday. So I must thank Dr. Shalu for the very comprehensive and take that in a very simple way. I'm sure most of you have learned a lot. Now go back to your drawing boards, read your books, and also when you are handling ventilation, try to also look at what concept he has tried to give. The concept is very, very, very important. Right. So thank you all. Wishing you all a very happy weekend. And Saurabh ji, once again, thank you very much for coordination. Thanks a lot.